it's time to get started, right? Okay, so good morning, everyone, or maybe good afternoon or good evening, depending on where you're at. It's my pleasure to introduce Yusuf Mroueh, who's going to talk about convergence of gradient descent and gradient flow.
Great. Thank you so much, Nadia, for the introduction, and thanks for the organizers for organizing this great workshop and for the invitation. So I'll be talking on the convergence of gradient descents in GANs, MMD GAN as a gradient flow, and this is joint work with my colleague Trion Nguyen. And so to start this talk, I'll be following this outline. I will start by a few motivation and introduction on what are generative adversarial networks. Then I will be talking about particle gradient flows, which will be making good link with the talk of this morning, if you were attending it. And then I will show how to go from particle gradient flows to gradient flows in the parameter space of a generator. So when we are living on a statistical manifold. And then I will show that once we are using this structure of optimizing using the MMD distance that we will define the maximum mean discrepancy distance that's defined in NRKHS, we need to define some Riemannian structure on it where this MMD becomes just a gradient flow on this particular Riemannian structure. So an introduction. So what is a generative adversarial network? So generative adversarial network that were introduced by Goodfellow in 2014, and they have been really very powerful generative models for many modalities such as images, text, graphs, etc. And the basic idea is that you have two players, the generator and the discriminator. So in mathematical terms, the generator is just a push-forward map that you push through it some noise, and then it will produce noise of lower dimensional, and it will produce a higher dimensional vector, right? The discriminator is, if you want to think about it in terms of optimal transport, it's the potential of the Weierstein distance or any distance you would consider, like let's say like the maximum mean discrepancy, or if you want to use F divergences, it's the potential function. It has different names across many different fields. So it's called witness function, critique, or discriminator. These are all the same name for the same object. So how does the game go? The generator goal is to fool the discriminator that he's producing real images. So in a sense, the discriminator sees the training set that is real images. Then we push forward the noise via the generator. We get set of fake images. The goal of the generator is to fool the discriminator that that it's producing real images. And the discriminator role is, like the police, is to tell apart which image is real or which image is fake. So as I was saying, as we are training our generative adversarial network, this is related to the optimal transport in its both forms, right? The static form, where like we're doing it in just one move, or in the dynamic form, if we see gradient descent, as the talk in the morning was saying, that we are the time of gradient descent will be the continuous time, and we are pushing our probability mass from the noise distribution to the real distribution. So how does the generative model start? This is how it starts, right? So what you're seeing here on this grid, each image here, it's a random image. And as we train the generative model will be starting to converge to the real distribution. So this is how it converges. So when we talk about convergence of GAN, we are talking about convergence in distribution from the noise distribution at start to the real distribution at the end. So when does this happen, and how can we ensure it happens? So again, the difficulty is that we have a generator, right? So we know if we don't have a generator, this becomes like moving particles, right? If I give you the density and you know the score function, it's very easy to sample using Langevin dynamics, and then you can analyze it, right? So this Langevin dynamics is just one instance of what is called the particle flows methods. And I will be discussing one methods for particle flows in particular, because it will help us to move to the case of GANs. So as I said, the goal is we want to construct a path, like similar to what we've seen in those animations, that takes me from a source distribution Q to a target distribution P. So we will be considering a reproducing kernel Hilbert space H with a kernel K. And then, as I said, we are considering a set of particles, right? The set of particles that starts from X0 that's sampled from Q. And then we are considering a sequence of potential Ft that are in the RKHS. And we consider the following particle flows, that is dxt equal gradient of those potentials, Ft's evaluated at xt dt. So we have this sequence in time. I didn't say what is the sequence. Then we will see how do we choose this sequence in order to ensure that we are moving our density from Q to P. And let's see how do we choose it. So assume that we have the initial distribution is this Q0, that is the heart shape. So every point into D here inside the heart is a sample from Q0, and we want to move it to the chicken or rooster shape in the target P, right? So how do we choose those FTs? So the way we will choose it, we'll choose it via this, as we saw here. So if I define the sequence FT, then I defined how the motion will be. So how do we do it? So what we will do, we'll consider a function F that has high values on the target function P, on the target density P, and low values on QT. So we are maximizing over this. And importantly, how we are regularizing this potential F. We are asking it to have a small gradient on the support of the intermediate distribution QT, and we are regularizing it in the RKHS via the norm in the RKHS. Oops, what happened? Hello? You still? Sorry. Do you see my slides now?
Yes, I do.
Okay. So what we will do is, so if this object should remind you the H1 minus the Sobolev semi-norm H minus 1 Q of T. So this is the approximation of this norm, semi-norm so this is P minus QT in this norm. We are approximating it in the RKHS, and this is what we call the it's a kernelized, if you want, Sobolev semi-norm. And this has since we are in RKHS, this has a closed form solution. So you can solve it with closed form to get the values of Ft. So at each time, I will be computing Ft and then moving my cloud of point with this, with the dxt. And then the mean field limit as n goes to infinity will give me a Qt, and then you can imagine how would this go. So what we can, let me show you how this goes in practice. So in practice, we will start from the heart, and then we are computing those gradient of Ft that you see in the arrows, and it's moving it to the shape of the rooster, right? So the level sets that you are seeing in colors are the values of this discriminator, right? Where it's yellow, it's saying go there. Right, where it becomes blue, it means that it's not the direction that you want to go through, right? So that's how things work. So what we can show is that those flows determined by this particular choice of Ft, they will be decreasing the MMD distance, and under some condition they will allow really the conversions to the MMD at the limit of T goes to infinity. So to put this in as I was telling you in terms of GANs, so it's really the two steps, right? So we have the discriminator update where we are seeking a function that discriminates between the real and the, let's say Qt is the fake distribution or the intermediate distribution. And then we have the particle update that is a gradient flow, right? So we are optimizing over this functional to find a Q such that I move from so that I move my point to minimize this discrepancy in terms of FFT. And how is this optimized? This is optimized with a gradient flow. So this really mimics how the GAN work, right? So in a sense, this particle-based method that's called Sobolev descent that we introduced, I think in 2019, it's very similar to the GAN. The only thing, it doesn't have a generator. It doesn't have a parameterization. It acts in the input space on the particles themselves. So the goal of this talk next is to show how can we move from the particles to a generator. Any questions so far? All right, I guess I'll continue then. So how do we move from particles to a parametric statistical manifold? So I will redefine things here to be more formal. So we have nu is a base distribution. It's a simple distribution such that uniform distribution or a Gaussian. G theta is my generator. So G theta takes a lower dimensional space and it gives me as output higher dimensional vectors that will, when I push forward the nu via G theta, it will give me a manifold that will give me some distribution Q theta. It's indexed by theta, right? In some parameter space that lives in the RP. So then my goal is when I want to learn a generator, G theta, I want Q theta to be close to a P in a certain form of discrepancy. So when I talk about statistical manifold, the statistical manifold is P of theta, which is the set of the Q thetas that are the push forward of nu via G theta, where theta is in the parameter space. So G theta is typically a neural network, but as you will see throughout this talk, it doesn't matter what is its parameterization. So G theta can be any function that maps the lower dimensional space to the high dimensional space of where we care about. We'll define the Jacobian as just the derivatives of the G theta with respect to the parameter space, d theta. So now, as I said, we will be working in a reproducing kernel Hilbert space. So we need to define a few objects that will be necessary for us to continue the method definition. So for probability distribution rho, the kernel mean embedding is nothing than integrating the kernel against the distribution that we have at hand. The MMD distance is then the distance in the Hilbert space between the kernel mean embeddings of the distribution P and the distribution Q theta. So far, what did we do? We just said that this discrepancy between Q theta and P, it will be the MMD distance. That is nothing than embedding those distribution in a Hilbert space via the kernel mean embedding, and then comparing those embedding in the Hilbert space. So what we know about the MMD, if the kernel was universal or characteristic, then if this MMD is 0, this means that P equal Q theta. So in a sense that it's a real metric. So it's if and only if, under those assumptions on the kernel. So the kernel needs to be universal or characteristic. So as we talked before, right, when we were doing the particles, right, so we needed something that takes me from the RKHS to the input space, right, because this is how I would move the flows of my particles. So since here we are in a parameter space, what we would need operators that goes from the RKHS to the parameter space and vice versa. So that's how the gymnastic will be to go from particles to parameter space, is via defining the operators that takes me from the RKHS to the parameter space, because this is how I would update my generator. And then I would need another operator that takes me from the parameter space to the RKHS, because this is how I would update my discriminator. So let's delve into what is the RKHS to parameter space operator. This is the L theta. So the L theta is an operator that takes a function in the RKHS. It gives me something in the parameter space of the generator. And it's nothing than taking the gradient with respect to the input of the function, evaluated as G theta Z, and then multiply it by the Jacobian. So this is the gradient with respect to theta in the by the chain rule. Now, from the parameter space to the RKHS, so this is giving a vector v, I want to get sorry, this should be L theta transpose of v. So L theta transpose of v, it is the gradient of theta of the kernel evaluated at g theta z times v nu dz in the parameter space. So this might sound now a little bit like why those operators, but as we go through the talk, it will become clear why those operators are important. So in a sense, the intuition behind those operators is that we will be using them in order to update the parameters of the generator and to update the parameters of the discriminator. So another operator to define here is the operator d theta that will be very crucial throughout the talk. It's equal to L theta transpose times L theta. And this is a positive semi-definite operator just by construction. So by construction, L theta and L theta transpose are adjoint one of another. And as I said, d theta is symmetric. The importance of d theta is in the third point here in this proposition. What it says that, sorry, the norm with respect to the norm of the gradient of theta of the integral of fx q theta x has this nice form that is f d theta f. So in a sense, the operator d theta, the way to think about it is just giving me a representation of this norm squared of the gradient with respect to the operator of the function integrated against q theta dx. So that's what is the operator d theta. I don't know why it's doing this. Sorry. So now if we take I'm gonna define now similar to how we defined this object here, right? This was crucial to define the velocity fields to how to move the probability mass. So we have to define a similar discrepancy, if you want, in order to define some velocity fields to move the mass defined by. And this is what we call MMD alpha beta. So it's again has the same form. So it's a function that has high values on the support of P, low values on the support of Q theta. And importantly, the way we will regularize, it's again using the gradient, but differently from what we did on the particle level, we have to take the gradient with respect to the parameter space, and the norm should be outside. It's not inside. It's not the norm of the gradient inside. This doesn't work. And we will, if we put the norm square inside, it doesn't work. And this, we will get to it why it doesn't work in a little bit. So since we are in RKHS, this has also a closed form where, because this first part can be written with the mean embeddings. The second part, as I said, it will be written with the operator d theta that we just defined before. And then the solution of this one is just a solution of this big linear system, right? Alpha d theta plus beta I, f equal mu p minus mu q theta. So beta here is a regularizer in order to ensure that this inversion does not run to problems of singularities. So far we have defined this MMD alpha beta. Let's play the same game that we did for the particles. So the goal is to construct a path theta t so that q theta t converges to p as t goes to infinity. So how we will do it, it's the same thing that we will do. We'll take a sequence of potentials ft and hk, and we'll consider the following flow in the parameter space, the following continuous flow. So remember, L theta was the operator that takes a function in the RKHS, and it will give me something in the parameter space. So this is the candidate that we will use for a flow in the parameter space. So d theta t dt is equal L theta t of ft. Now we'll play the same question, which ft to use, right? So in order to do that, the first I will walk you through how we will determine which ft to use. So once I have my theta in the parameter space, I'm moving following this dynamic. Let's see how the generator dynamic changes for a fixed z, right? For a fixed input z to the generator. Let's see as theta changes how the dynamic of the generator changes. So then by the chain rule, this is nothing than the Jacobian multiplied by the dynamic of the parameter space. Then if I put the expression of the L theta parameter inside, this will become this G theta Z prime times the gradient of G theta Z prime nu dz. So let's call this product of the Jacobians by its transpose at 2 points as a kernel gamma theta t z prime. So this is a kernel that is comparing 2 points in the hidden space of the generator z prime, and this kernel is matrix valued, right? So it has the dimension d by d times the gradient evaluated at z prime, g theta z prime nu dz. So this is now very interesting because this tells me while the dynamic when I was dealing with a particle, all the points were independent, how they move. Here they are coupled via this kernel, right? So how a point g theta z moves, it depends how this kernel sees z close to z prime, and it's the mean of the dynamic on all other points. So it's the average weighted of all how the velocities for moving all other point dz prime. So that's interesting to realize that it is now the dynamic of the generator with respect to the dynamic of what we've seen for particles. It's a coupled dynamic, right? And it's coupled via this important object gamma theta t z prime. Now I have the expression of how the generator dynamic is. Let's see what is the dynamic of the mean embedding, right? And why are we doing the dynamic of the kernel mean embedding? Because we want to see the dynamic of the MMD at the end. So the dynamic of the MMD, it's again this derivative of the kernel evaluated at g theta tz. We are integrating it over all news. So then again, by we're assuming that the kernel has the nice properties to be able to exchange derivatives and as well as the generator. So then we will get the derivatives inside, and then again we will apply the chain rule, and we'll get the derivatives of the dynamic of the generator, right? Then that we just derived before. If we put its expression, then we will get the as I was saying, the kernel of ZZ prime, the gradient at GTZ prime, and apply it to the derivative kernel. So if you trust me, this is the expression of the d theta t applied to ft. So this is the operator that we introduced, that is L theta transpose. So this is an operator from H to H. We apply to it a function in H, and it will give me a function in H, right? So the nice thing, so think of this in terms of the particles. I like to think of this as similar to the continuity equations. So this is a easy, it's an equation of the kernel mean embedding. So it's an equation of how the kernel mean embedding evolves in the Hilbert space. It has, in this case, this very simple expression that is just an operator d theta t applied to a function ft. Now let's go back to the MMD. So the MMD, recall, it's just the mu p minus q theta t. Since we have now the expression of the derivatives of the kernel mean embedding, it's very simple to derive the expression of the MMD dynamic. So it will be just the mu p minus qt minus dt qt, and this is the final expression, right? So if we look at it, this is telling me if I want to choose my ft, I should just choose it to be this way, right? d theta t ft equal mu p minus q minus mu q theta t. Because if I do it, then I will just get df qt dt is equal minus 2 f qt f minus the MMD, minus 2 of the MMD, which means that I'm getting an exponential convergence. So this is interesting, but it has a caveat, right? That d theta t might be singular. So because d theta t may be singular, then we have to regularize our choice of d theta t. And then if we regularize it and we put alpha d theta t plus beta I f of t, then we will get the witness function of MMD alpha beta that I defined before. Remember this one, right? Sorry, this one, right? So this is the witness function of the MMD alpha beta of this that has this form. So in a sense, in order to be optimizing to be decreasing the MMD, as we saw here, if we choose this, we would get an exponential convergence. But the caveat is that the solution FT may not exist, or it may be I have infinite number of solutions. Then we fixed it by adding some regularizers. Then the question is, how does the MMD evolve when I use this type of sequence? And the answer is, if I apply this dynamic, right, my d theta t changes as the operator L theta t applied to ft, where ft is the solution of this form, and then I update q theta t via pushing forward the distribution nu via g theta t. Then what we will get, this is the first result, is that it's indeed decreasing. We will lose as you see, the exponential convergence. There will be a damping term, and the damping term is proportional to the MMD alpha beta. Now, when this is strictly decreasing, it's strictly decreasing if my difference of mean embedding is not in the null space of the operator d theta. And this we will understand it as we move forward in the talk, what it means. So why this condition is important to not have the difference of mean embedding in the null space of the d theta t. Any questions so far on this section? Okay, so just to recap what we just saw. So in order to get meaningful potential functions to move my discriminator, we saw that we need to define this witness function of this MMD alpha beta between distribution, that in this case, because we're considering an RKHS, it has a closed form solution that has this form. Then the generator update, it will be just take this FT and do your gradient flow with L theta t FTDT, and then update your distribution Q theta t via the push forward map, and then recompute your FT and so on. So this is the process that will lead to this decreasing of the MMD, as we saw in the previous theorem here. Now, this was in the continuous flow, right? So now we need to discretize it because we want to get an algorithm that we can implement. So in order to prove anything for the discrete case, we need to add additional assumptions on the kernel and on the generator. For the first, the kernel needs to be Lipschitz, and as well as its derivatives. And same for the generator. So it needs to be Lipschitz in the parameter space, with DZ has a finite second moment, as you see here. And the same for the Jacobian, it needs to be also Lipschitz. So if we make those assumptions under suitable choice of the first parameter theta 1, actually, I forgot to talk about this in a more detail. So as we discretize here, so the discretization means just that we go from DDT to a pure gradient descent, right, with a learning rate epsilon L. And we will make this change that will also make the regularization adaptive. So at each time, we'll be choosing a new regularizer, alpha L and beta L, that will be chosen, actually, I will not go through the detail, in such a way that the difference of mean embeddings is never in the null space. So this will choose alpha and beta in order to satisfy this assumption. If we do that, then we are guaranteed to have this type of convergence that is for the discrete case. So once we discretize, we needed extra assumption on the kernel and on the generator, and we need assumptions on the initial condition, as well as the learning rates and the alpha L's and beta L, the regularization, in order to ensure that we will have this type of exponential convergence. So how does this work in practice? So here the goal is to move this Gaussian distribution here in blue to this mixture of Gaussian that is in green here. So in the first panel A, we will be using those flows, but with alpha L equal to 0. So in a sense, this will be just an MMD regularization, right? So will not be using any alpha L. So it will be using just the difference of the means to move the flow. So as you see from here, this is something that will never converge. It will be always going through cycles. And this is known in GANs as the mode collapse. Now, if we use alpha different from 0, alpha is 100, then what you will get is that you will be converging very fast to the distribution and getting all the modes. And you see this type of behavior in the convergence. So the difference between panel C and E is that here the discriminator was really in the RKHS, that it's just a linear weight that is computed with closed form. In the E, here it is a neural network that is also learned. So you see it has very similar behavior to the kernel method, which may be indicating that there is possible analysis when the discriminator is also a neural network via some tangent kernel theory, probably. So this ends the second part. I'm happy to take any question if there is on this part before I move to the last part of the talk. All right. Any question? Okay. Okay. So to as we saw, like here, what we did, we just said in order to move from particles to something using generator and parametric generators, what we needed to change how we get those, how do we regularize our MMD distance in order to get meaningful directions in the parameter space. This went through defining MMD alpha beta and all those operators in order to get convergence in the MMD sense. And again, convergence in the MMD sense will mean convergence in distribution if that kernel was universal or characteristic. So the thing that is a little bit hard to understand here is that the way we defined MMD alpha beta and the way how we defined all those operators, it went really going via the dynamic of the MMD, but I went through it with you, right? We defined how the generator changed, and then how the mean embedding changed, then how the MMD changes. But this seems that as we are defining a natural gradient on the space, on this manifold on this parametric manifold, similar to how we do, for example, with the KL divergence, how you define the natural Fisher gradient or things like that. So the next section will be trying to understand how the object that we defined in section 2 from this perspective of defining some Riemannian structure and seeing that if we can define all what we have done so far from the lens of gradient flow with respect to a particular Riemannian structure. So to remind you a little bit of some known Riemannian structure that we know, it's the dynamic form of the Wasserstein 2 as defined by Benamou and Brenier. So this will be very similar to what we've been defining now, right? So you want to find velocity fields that are gradient of potentials Ft, right? That have the minimum kinetic energy. So this is a velocity square times a mass. So this is a kinetic energy that I'm integrating across 0 to 1. And then I'm moving my mass via the continuity equation, right? Starting from a distribution Q, ending in a distribution P. So in principle, this is similar to what we've been doing, but it's not the same because we're not following the continuity equation. We are not minimizing this form of kinetic energy. So we'll try to mimic the Benamou-Brenier in our case and try to define a new structure. So the new structure that we will define, we call it this d alpha beta. So again, as I was saying, the continuity equation, we will replace it by the dynamic using the operators that we defined, right? d theta t is equal L theta t ft. Ft is in H. The initial condition, it will be, since we are on this manifold defined by the generator, right? So it will be for theta at time equals 0 equal theta 0, and theta at time equal 1 equal t1. Then which energy are we minimizing? So we need to minimize a The first one is, if you remember how the mean embedding changes, the mean embedding changes via this d theta t ft. So in a sense, this is the velocity in the RKHS, this first term. The second term, it is the velocity in the gradient, in the parameter space that has a nice form in the RKHS, ft theta t ft. Okay, is this clear? So the way we will mimic the Benamou-Brenier dynamic form is via defining some form of the which energy we're minimizing. So it's an energy in the RKHS, an energy in the parameter space. The dynamic, it's the equivalent of the continuity equation. It's nothing, it's similar to how we define the dynamic via the L theta operator. We have restricted the functions ft to live in the RKHS. And we are defining theta 0, and theta 1, theta 1. So while for this type for this type, it's not easy to find existence conditions or things like that, but we will use it as a guide to define the Riemannian structure. So this is it needs much more work in order to find the existence of those FTs and theta t. So it needs some extra conditions on the generators and as well on the kernel. So the way we will define the Riemannian metric tensor inspired by this form of distance is that we will be as it's usually defined, right? So you will get from this the product, and from this the product for two elements of the tangent space, sigma psi 1, psi 2, where psi I is equal L theta phi I. Phi I is a function in the RKHS. Then we'll define it alpha d theta phi 1 d theta phi 2 plus phi 1 d theta phi 2. And it will be written in this compact way, right? So this is the Riemannian tensor metric. And as I said, the way we defined it so that it becomes really a Riemannian metric via integrating the tensor metric on the infinitesimal motions of d theta t and with ft in h. So once we define this, we can define the gradient flow with respect to the alpha beta, right? So once we think about the gradient descent with respect to the parameter space, we think it's a Euclidean gradient. But the way here we will see it, we'll see that we want to define the gradient flow of a functional that lives on the statistical manifold with respect to this d alpha beta, right? So the way we will define it is as it's usually defined once we have defined the metric tensor, right? And this dynamic form. We'll define it as, so the gradient flow is defined via this, right? So if I take all the curves that are theta that are going at time equals 0 by theta, and they have in the tangent space at t equals 0, it's equal xi. Then once I compute this derivative at time equals 0, I can read out what is my gradient flow. What's my gradient of my functional f theta? Again, f here with respect to the usual how you define it for W2, it's defined on the parametric statistical manifold, right? So we'll define it with respect to d alpha beta. So once we define for certain functional that have this form, that are function of the mean embedding at q theta, for some functional h with this following chain rule that holds for it, then the gradient flow has this closed form. So it is equal to L theta of u, where u solves this linear system. So this is, you start to see similar to what we've seen for the MMD. So again, if I follow now the gradient flow using this minus L theta ut, where ut is the solution of this, assuming my generic functional has satisfies those assumptions, what we can show that similar to the MMD, I will have these are decreasing directions. So in a sense, it's a descent direction. Now to open up what is going on, like what is this d theta t? I'm gonna write I will consider the eigenvalues and eigenfunction of d theta t and write the solution ut in terms of the eigenvalues and eigenfunctions. So it will have this form, right? It will be expanded on the eigenvectors the eigenfunctions multiplying by h theta, and then this is the inverse of that is regularized. So the gradient flow is then written in this way, right? So it is written in this way. Since L theta is linear, remember the gradient flow is just L theta ut. Since L theta is linear, I can just push it to the function Vj, and I will have this. So then the gradient flow is the sum of those principal velocities, right? So the operator d theta is giving you all kind of velocities once you apply L theta to them in the parameter space to move, to go towards the direction that you want. And then this h theta is nothing related, it's related to the gradient in the parameter space. You are seeing how aligned you are with the direction where you want to go. So when we were saying that h theta in the case of the MMD is the difference of the mean embeddings. When we were saying we don't want to be in the null space, because if I am in the null space, I will not be able to move, right? So because I cannot express my directions Vj in the range of the operator d theta, because it's giving me all the direction that I can follow. So that's very nice, because this tells me sometimes if I have what is called mode collapse in GAN, it means that I ran out of like my d theta, the reservoir of velocity is not able to move me towards where I want to go. So remember, so just to recap what we've seen here, so for functionals that are written in terms of the mean embeddings, the gradient flow with respect to the new Riemannian structure we defined, it has this form. And then the gradient flow expression is just this one. MMD is nothing than that. So this is how we defined in the second section of the talk, right? We say take d theta, L theta, ft, and then compute your ft via this, and then do your push forward. All this can be written in an equivalent compact way as just the gradient flow of the MMD distance with respect to this new Riemannian structure that we defined. Just because, as I said, h theta in the case of the MMD is nothing than the difference of the means. So this is a nice perspective on MMD GAN, because it tells us how do we see it from a gradient flow in the parameter space with respect to the correct type of Riemannian structure on the manifold of probabilities. And this is not only, as I said, this is applicable to any functional on the statistical manifold, as long as it can be written in terms of the mean embeddings. So I will give here a few examples, because this tells us that if I have now any functional and I want to optimize with generators instead of doing particles methods, I can. For example, potential functions, right? If I have a potential V integrated against Q theta, then the gradient flow has also a closed form. If I take also an entropy, but in the entropy, it's defined here differently than the usual case. So we replace the density by the mean embedding of the density. So then it will have as well a closed form solution. For the interaction energy, it's also different from the usual case. So it's fxgy. And again, we are writing it this way so that we can write it in form of mean embeddings. Then it has also a closed form solution. So in this talk, what I started by introducing is how do we do particle flow methods for the particles case. And then we show how do we define a new discrepancy, this MMD alpha beta, to define directions to steer the generator towards the distribution that we are interested in via using kernelized parametric gradients. And we saw that this holds to go from the continuous to the discrete for assumptions on the kernel and assumption on the generator and suitable choice of learning rates and regularizer. Then we show that we defined a new Riemannian structure on the statistical manifold that is defined by the generator. And we showed that the MMD alpha beta flows coincides with the gradient flow of the MMD with respect to the Riemannian structure. And via defining those general flows on this statistical manifold, it opens the door to use those generator parametrization in order to optimize other functionals like the ones I was defining, the entropy, interaction energies, and the potential energies. And thank you for your attention, and happy to take any question.
Thank you, Yusuf. Are there any questions?
Can I?
Yeah,
it's really this is quite interesting. You know, a lot of interesting ideas. Somehow the description of the statistical manifold that you're using, somehow, and the importance of what generator are using, that kind of went by a little bit quickly for me. So could you maybe elaborate a little bit as to what kind of parameterization of your manifold you find to be advantageous?
Yes. So the generator G theta is any function that maps this lower dimensional space to the higher dimensional space of interest where my distribution P lives. So the main assumptions that we need on the generator is, and I will explain them why you need those in an intuitive way. So these are the assumptions. So the generators needs to be Lipschitz in the parameter space, right? So that if I choose two different thetas, right? So I want to be so remember the gamma theta ZZ prime, right? So let me say this one here, right? So if this gamma theta ZZ prime was delta ZZ prime, right? If it was delta ZZ prime, what this means, it means that I'm back to how the particle space was, right? How like everything is independent. So this Lipschitzity, it will ensure something like this. It will ensure that when I move, I'm very close to the particles, how the particle move. But it's not exactly the particles. Because remember, this is the distance gamma G theta Z prime. Like it is similar to a distance between G theta Z minus G theta Z prime.
Right. I guess I would need to read the details in your preprint. So your preprint on this is what you refer to at the end, right?
At the end, yes. Yeah, this is the preprint.
Right. Okay. Thanks.
So the main thing is that we didn't consider very strict any conditions on the generators, except we will need those ones when we move to the discrete case to prove anything about conversions, because there, like, you will have to bound a lot of things, and if you don't consider the Lipschitzity, things fall apart.
Right.
Thank
Thanks.
you.
Thank you.
I also have a question. So could you go to the experimental validation slide?
Yes.
So it looked like the MMD loss was the same or almost the same for figures D and F, even though you're using a fixed kernel and a learned kernel.
Yes.
Could you elaborate?
Yeah. So here you see it's less smooth, while here it's like going down like in a much better like you need to zoom in probably to see it.
Okay.
So once you learn the kernel, it seems that it has much nicer behavior than once the kernel is not learned. In any case, it was a surprise for me that like only a linear, like just for a fixed kernel, things work. So here the kernel is not learned for this in this case. So here it seems that like maybe one needs to do a la Shiza-Bach, or like what the earlier talk today was saying, in order to analyze the setting of E, where the kernel is learned.
Thank you.
Yeah, and if I mean this work is still new, so if you have any feedback, don't hesitate to email me.
Okay, and I also have another question. There was exponential convergence of the T to T. Was this surprise? Is this surprising to you, or like?
So I think it is. How do you? I think of this d theta operator that it's similar to a conditioning, right? It's similar to like it's similar. How should I say? it's not a second order method, but it seems almost like putting the right conditioning to like on the gradient descent for it to converge better. So remember, like the difference between the not like putting alpha equals putting this regularizer or not putting it in terms of here, right? So if alpha equals 0, the function that you're using is just the difference of the mean embeddings, right? If alpha is positive, then it's d theta minus 1 mu p minus mu q theta. So my interpretation of what is going on is that this is giving the right conditioning so that the distance goes down correctly.
Okay.
I have a question with regard to the regularization parameter beta.
Yeah.
Have any ideas on how to pick beta in that formulation?
That's a very good question. So the beta, if you want to choose it, you want to look at the spectrum of d theta, right? So you could choose it probably as the median of the spectrum of d theta, right? So remember in the expression of the gradient flow when I wrote it here, sorry, give me a second, here, right?
Okay.
So here it depends on how much you want to spectral filter your operator d theta.
Yeah, I see. Okay, so actually you target the smallest singular eigenvalues in this case.
Exactly. So you can set it as the smallest singular value.
Yeah. I see. Thank you.
Thank you.
If there are no more questions, let's thank yourself again.
Thank you a lot. Thanks a lot.
And just so you know, the next